Thursday night, 6 o'clock. Must be time for a soaring seminar. Hope everybody's had a good week and or good 2 weeks since the last one. And here we go. Alrighty, so tonight, March 12th, Speed to Fly. The presentation's recorded and will be available on the SSA's webinar location. So here's a pointer to it for you. We had a little hiccup from the last session, and so we'll be getting the slides from the last session up uh, soon, probably about the same time these slides go up. One thing about tonight's presentation, it's even in preparing the materials a while back and going through them periodically for these seminars, the material in this presentation is not likely to be comprehended completely the first time through. So please download and review the materials. That will help. And as always, with one of my presentations, there's a lot of information in the recording that doesn't show up on the slides. So especially for some of the more technical areas of this topic, getting the audio recording may help as well. Our normal acknowledgments to the SSA and especially to Frank Whiteley for being our uh, little guru in the background that keeps this thing up and running for us. And our Wings team, these folks make the seminar sessions eligible for Wings credit. So if you registered for the seminar with your Wings user email address, then you're set up and will be applied automatically. The FAA guidelines allow credit for the online seminars, but it's only the live seminar that can get credit. We have some of our instructors. These are the four that some subset of this four are always sitting in the background. If you have questions, you can use the Q&A function and they will get to you. If it's a question that's more broadly needs a more broad response with an answer, we'll cover it in the Q&A at the end. And if it's particularly appropriate at a particular spot, they'll interrupt and we may handle it at that spot in the presentation. Subject matter expert acknowledgments. A lot of the information about pushing MacCready beyond just interthermal contest flying caught my interest when John Cochran did a Speed to Fly webinar a few years back. So here's a link to that webinar. By the way, I checked all of these links today and they all still work. Wings and Wheels has Speed to Fly articles in their collection of things that they send out. You know, they have a little newsletter that's worth subscribing to. And then Paul Remdy created a polar exploration spreadsheet, which you can download by following that link. And I found it to be really useful. In fact, all but one of the graphics in this presentation can be produced by using Paul's spreadsheet. So what you're looking for with this topic is you're looking for that aha moment when it all comes together. It might be in a class, or it might be reading quietly. It might be while you're in the air, and it might be one of those things that you wake up in the middle of the night and you go, wow. A special acknowledgement. Some of you may have known John Campbell. He and I used to teach at the colleges. There's 3 colleges on a huge campus in downtown Denver. He taught at one of the schools and I taught at another one. And very often in the evening after we'd taught our classes, we'd get in one of our offices and sit there and just talk about soaring. And John was my instructor for my winch rating. In 1969, John was in Hawaii getting his glider pilot's license, and I, at 16, was in Virginia trying to get my driver's license. I think he chose the better path. John founded the Collegiate Soaring Association He's the reason the SSA Junior World Championship Team program exists, and along with Jack Bushman's the reason the modern CAP Youth Glider program exists in Colorado. I've got a little thing up here for him uh, talking about search radius in gliders. I don't know where he came up with this, but this is one of the topics that we would bounce around. And that is at 20 to 1, cross country becomes consistently possible in terms of what you can, the radius that you can search for your thermals. At 30 to 1, it becomes likely, and at 40 to 1, it becomes close to certain. And that just has always stuck with me. All right, so tonight's session, it is the longest in our series this year, and I apologize. Most of ours are, somewhere an hour 45 to a little over 2 hours. This one probably will run about 2.5 hours. That's just for folks that are planning their the remainder of their evening. In this year's first session, the Intro to Cross Country, we discussed a training approach that utilized the proving grounds that was developed by the members of the QNIM Gliding Club up in Calgary, Alberta. The Black Forest implementation has a simple four-leg task with the turn points at a 5 nautical mile radius out from the airport as the racetrack task in the proving grounds. And it's roughly 50 kilometers around the task, plus the distance to and from the start and finish point, making for a total of about 70 kilometers. This is the first cross-country that most of our cross-country flying that most of our members are exposed to. And the gliders that we've used for this over the years, a K-21, a PW-5, a Russia, and our Blanik. All of these are roughly 30 to 1. So, just for oversimplification, we considered them all not the Blanik, but the other three types as 32 to 1 gliders. And we set up the rules for the racetrack to use, using the bronze badge guidance at 16 to 1 glide ratios, and we gave them hard decks. And the whole idea behind a lot of this was to take away some of the more difficult decision making from early cross country. We continued on, and our system has a couple of longer tasks that can get out into the range of 165 kilometers, including one that has a silver badge leg. And then we offer mentored flight in our K-21 with an experienced cross-country pilot using these tasks. So what happens is then, our members can have seen these tasks on mentored flights. So this is going beyond having all of those rules set around. This is now reaching into the decision making that you have to do when you're going somewhere beyond the boundaries of the proving grounds system. So most of what we're going to discuss this evening, I learned in my first glider years and years ago, forgot a bunch, and then I relearn it and rediscover it every few years. So we're going to talk about a philosophical discussion on the speed to fly. We're hoping to gain an understanding of it and illustrate its use. This isn't about racing or record flying. We're still addressing the needs of an early cross-country pilot with the goal of helping these pilots move to an intermediate or higher level of cross-country flying. This requires an understanding of the glider performance and how to apply that knowledge. This is in-flight decision making. The training wheels, like I mentioned, that we had under the proving ground system that we use for our very early cross-country stuff in our club, are loosened or possibly removed altogether. So this is, this is where speed to fly, you get an understanding of that, and you're on the way to longer cross-country flights. This is decision making, and interestingly about speed to fly, this is definitely decision making with uncertainty because you're going to have missing or erroneous data, maybe an incorrect transformation of the data, and you're going to have incomplete information. So this is the whole thing is there's uncertainty involved, but if you've got a strategy and a process, you can overcome a lot of the uncertainty. Now there are three speed to fly strategies that we're going to talk about. The original was for cross-country flying with the idea of improving cross-country speed, especially in a contest setting. We're also going to talk about final glide because there's a separate strategy for speed to fly for final glide. And then there's a strategy which is a subset of the final glide, and that's if you're in the area of unlandable terrain, trying to figure out if you can get across it or if you've stumbled into it. I say stumbled, realizing if you're truly in dire straits or uncomfortable over unlandable terrain, how many mistakes have you made leading up to that point? So that's also something you have to think about in your growth in cross-country flying. But flying in an area where the consequences of having to land out are very, very serious, there's an adaptation to speed to fly strategy that can support the decision making under those circumstances. Paul McCready uh, was I guess, the father. I don't know if he's the one that, as you can see from the arrow, he developed and refined the theory of optimized flight between thermals. That's what we call McCready's theory of speed to fly or McCready theory. He also developed a speed to fly cockpit aid using what we call a McCready speed ring that's based on the glider's sync rate at different airspeeds and depending on the conditions that you're in. And I'll show you that just so you can see, in case you ever stumble across one, you at least can recognize it. You can see what where he contributed uh, to soaring, and you can see some of his background. Now, there are an awful lot of other accomplishments in Paul McCready's lifetime. I'm just highlighting the ones that are related to our topic this evening. Traditionally, uh, McCready theory has been contest focused. And what you have to remember is that contests are an abstraction of real life. So in a contest, we're trying to, we're quantifying our performance and who has the best performance wins. For basic cross country, you know, did we make it home today? So you can see where there's an abstraction there. The other one is a contest way back in the day was wafting off downwind at best glide speed or minimum sink speed or flying a course at best glide speed. The other one is that it assumes roughly an equal distribution between climb and glide. And short-term goals are expressed as a number. We call it the McCready number or just McCready, excuse me. And it's the expected lift in the next thermal. How do you know? You don't. It's very much like lift bands that we've discussed previously. It's a guess based on what you see for the day and what you see along the course line. So it's also going to evolve during the day. You might start with a basic guess at when you first get off in your first thermal, and then as the day progresses, you build up a more and more accurate model of how the day is going to behave in your mind. So the goal here was to optimize the non-climbing phase of flight. Very limited number of parameters, basically just a couple of things that you could keep track of in your head. Short-term goals, and by that I mean thermal to thermal. And we're also talking about aircraft during this time period that had limited performance and very limited ability to affect the mass of the glider. In modern speed to fly, contests are becoming less and less important to the overall soaring population. So this is casual cross-country flying, or it might be record flying, but that's not our topic this evening. Basically, your goal is to fly fast enough to achieve your day's goal. I want to do I want to do silver distance today. I want to do a 300K. I want to do a 500. I want to do a 750. I want to do an out and return, a triangle, that kind of thing. And the bottom line behind all of this is that most of us would prefer not to land out, and if we did have to land out, we'd prefer to land in an improved location. One of the things that we have equipment that supports a broader range of parameters, the cockpit computers and the flight instrumentation that we have, especially with the variometers that support speed to fly calculations. but our expectations now are more qualitatively driven. Did I have a good time today? Did I make it around? Okay, you still may be chasing records or you may be chasing a personal best, but it's not the pure contest focus. And then the other thing which got John Cochran's presentation got me onto was the safety adaptation of speed to fly, especially for final glide, and then if you're in an area of unlandable terrain. So the inner thermal speed to fly. So this is a total drag polar. This is the overall aircraft's polar. For pilots, the limit on the left side is the stall speed, and on the right side is VNE. Now that total drag curve starts to look kind of familiar. So the drag force on the vertical axis can be related to vertical velocity. If we do a translation on the vertical axis from force to vertical velocity, the graph moves from quadrant 1 to quadrant 4 in the Cartesian plane, and we get this. Okay, so we're modeling the aircraft performance. We're working on good enough as opposed to absolute accuracy. This particular curve is often modeled from a quadratic equation. Don't let that turn you off. Don't worry about it. You know, Paul's spreadsheet handles however your flight computer wants the inputs and creates the tool that you can use. Um, One of the things that this will point out this evening is that from a pilot standpoint, in most cases, anything to the right of the decimal point is probably unimportant. We're going to be using graphs. I'm not going into the math behind any of this. Go play with Paul's spreadsheet if you want to get some of the mathematical insight. Like I said, he did an excellent job. I had one very similar that I developed, and then he popped his out for more general usage, and his is easier to use than mine, so that's why I point people in his direction. We first, probably as a mass consumption, we first got the thing about using a quadratic equation from Reichmann's cross-country soaring, which was the Bible on instruments and performance when I started flying gliders in the 80s. And it's still a very useful book. And I have seen it published online in a PDF form, but it's something that ought to be in your library, and you should peruse it. Uh, and if you got some serious questions, it gets kind of useful. For most sailplanes, the useful portion of the curve is from the minimum sink speed to the speed corresponding to 6 knots sink, which is usually well into the to the yellow arc. Now that may be shifting somewhat with the modern 18-meter gliders like the JS3, the Ventus 3, and the AS33, because they've done some other work structurally and aerodynamically, so uh, the yellow arc may not be in where you normally think of it if you're flying an ASW20 or a 19 or an LS3 or an LS4, those kind of aircraft. One of the things that you'll find when you look at this is flapped gliders will be um, flap gliders will have a flatter curve over here on the right side. A standard class glider somewhere out here, dry around 80 to 85 knots, the curves will start to diverge, and a standard class glider's performance will decrease. Heavyweight, it still happens, it just happens at a later speed. Um, the thing that happens with the higher performance gliders uh, starting with the ASW20 and Ventus, so mid to late 80s type aircraft, is this curve flattened and it moved to the right. So an earlier curve might be something like this over here. All right. Unballasted, this is a dry polar, and all of my examples on the polar this evening will be from my Venice B that I used to own, just simply because I went through all of this trying to understand its performance, and then so I had all the numbers generated, and even though I'm flying a different glider today, I used all of this information. I just didn't have to go back and do it and learn it. And I was just able to apply it, which is one of the things. You get a good feel for this, and as you move from glider to glider, you can apply it to the glider that you're flying with once you can understand the relationship that this curve represents. There are aircraft out there that have a polar that you can't get a real good match on a quadratic equation. And of course, I say that, and then you know, remember my thing about modeling is that all models are wrong, just some are useful. And the quadratic equation or quadratic approximation that we use is not perfect, but it's good enough. If you ever want to get an idea of how wild the data can look, go back and read some of Dick Johnson's articles where he's measuring the performance. The amount of scatter in his data is impressive. And there have been people over the years that have been upset about the curve that he generated as a result of his data, but it has been good enough for us to use in making decisions. Okay, one of the things we're going to do, let's start turning this into some useful information. So we're going to draw a line from the origin. So 0, 0 right here. We're going to draw a line from the origin and have it be tangent to the polar. So it's going to cross the polar and touch it at only one point. And of course, the graphics, it's limited. It looks like it munges on a whole bunch of it, but we'll bring it down to a single point. So right there. Okay. So that's the point on the polar in a calm atmosphere. That's the best lift to drag ratio that you've got, your best glide ratio. Okay. And so from there, if we go vertical, in the case of my Ventus, that's 53 knots. That is the best glide speed for the Ventus. And if we go horizontally back to the scale on the left, we now have our sink rate. So if I divide the horizontal speed, 53 knots, by the sink rate at 1.23 knots, we get a glide ratio of 43 to 1. Okay. Now, if one flies at the best glide speed, and this was one of the this is the observation that McCready made, what we're working on now, that becomes the basis of how can we improve our speed to fly or our speed on course. So if we fly at the best glide speed, what's our achieved cross-country speed? All right, so now we're gonna look at this and say no wind, and we're flying on the course line, and we're gonna say, let's say for the day we did our flight, we came back and we said, this was an average 2-knot day for the entire day that we were in the air. So we come up here on the horizontal axis and we get to crossing point for 2 knots down to our speed to fly. And McCready's observation right here was that our cross-country speed would likely be somewhere in the neighborhood of 32.5 knots. Forget the part on the right side of the decimal point. And if we take our 53 knots and our 32.5 knots, we find out that we're moving forward 61% of the climbs. So we spent 39% of our time climbing. Now, this also has the generalization in it that the sink and lift are roughly evenly distributed over the entire flight. So some really confining or simplifying assumptions with this. But this was one of the things that he observed, and then from there he moved on. But now, so we're going to go out and go fly at our best glide speed. How far can we fly at our best glide speed? Okay. So I've taken it and done it 1 hour, 2 hour, up to 9 hours. If you look at 3 and 4 hours, so a typical contest day is 3 to 4 hours. So basically, we would get somewhere between 98 and 130 nautical miles, or 181 kilometers, or 240 kilometers, or 112 miles, or 150 statute miles. Okay, I play everything in nautical miles because that's comfortable for me, and I can make decisions. I can do arithmetic in my head in nautical miles. Okay, so now the only reason I'm bringing this back to contests is because it does illustrate what we can do. Contest pilots routinely do 500 kilometers. Okay. So somewhere in the neighborhood of 200 and, between 400 and 500 kilometers. So somewhere in the neighborhood of 220 to 270. So down in this range. But they do that in 3 to 4 hours. So obviously they aren't flying the best glide speed on the glider. The other thing that I want to remind you of is when we did the intro to cross country, I said your first 300-kilometer flight is going to be roughly 5 hours. That's one of the things I said. Unless your club requires it to fly their gliders cross country, don't worry about your 5 hour flight. You'll get it when you get your first 300K. And notice that, that falls right in with flying best glide speed right there. So if you start to look at 500 kilometers, which would be down here in the 270 range, so 300 kilometers, take off at noon, be back by 5. Down here, take off at noon, be back around 7, or take off at 11 and be back around 7. Okay. Now, my first 300-kilometer flight was around 5 hours. My first 500-kilometer flight took 6.5 hours. So obviously, I improved my cross-country speed between my first 300K and my first 500K. So the goal of McCready's theory was to improve cross-country speed in a contest setting. So all of this points out is that we fly faster. So McCready's idea was to fly faster than the best glide speed. And so what he did is he said, well, if I fly faster than my best glide speed, I'm going to end up thermaling less. My cross-country speed should improve. Okay. And so as we play with this, so there's the best glide speed. Now, as we're playing, if you go out searching for information on McCready, and you go see some of the original papers and that kind of thing, and remember for the time period that he developed this, the speed range between stall and V&E was much less in 1950 than what it is in a modern fiberglass carbon composite glider. And the mass of a modern glider can be varied over a much larger range than a typical 1950s glider. And those two things make a real difference in how we use this. So if we're looking at this, if we start playing with it and go, okay, so if I were to draw that tangency from a 1 knot point and carry it on out through, well, we'll go to the top of the scale over here to 5. So at 1 knot, it's 43 to 1, and we're flying at 53 knots. At 1 knot, we're now up to 63 knots and 39 to 1. And at 2 knots, we're up to 72. And we're at 36 to 1. At 3, we're up to 80 knots and 32 to 1. And at 4, we're up to 87 knots and 29 to 1. And at 5, we're up to 94 knots and we're flying at 26 to 1. Okay. So these are the best glide speeds if the day, if the lift supports that kind of, or, if the atmosphere supports that kind of lift. Okay. So you want to shift, you know, we want to think of this in terms of expected lift. Okay. When you were taught this in your private lessons, you were probably taught that that's the speed, this is sync. Now, I want you to think about this in terms of expected lift in your next thermal. That starts to be the key. So those numbers become the McCready numbers. So that's where 0 through whatever, that's where those numbers come from, is from doing this kind of an analysis. So what I was just saying out loud, here's a slide that has it. This is where the modern usage also, because they were concerned, as you'll see in a few minutes, they were concerned about the increase in cross-country speed, but we also want to track the glide ratios because those glide ratios become important when we start looking at the safety glide. So the final glide or the safety aspect of unlandable terrain. All right, so this is a polar with a best glide, and again, all of this is based off of my Ventus B. This is a polar with the best glide with the tangent at McCready 4. And so at McCready 4, it's 87 knots, and our glide ratio is now 29 to 1, but we're really cooking. So, maybe that's not that important. If the day's good enough that I can fly 87 knots, then the fact that I'm now 29 or 30 to 1 glider instead of 43 to 1 glider probably doesn't bother me that much, especially if it's a tall day and I'm in that top lift band. So now we play the game of what's that crossing point? And the so here's the crossing point. And now our cross country speed went from 32 and a half at the best glide speed to 50 knots at this speed, at our McCready 4 setting. Okay. And then the other one is, let's also take a look, because you've always heard the thing about speed up and sync and slow down in lift. Okay, now I've arbitrarily on this curve added a line 10 knots slower, or a point 10 knots slower, and a point 10 knots faster. And notice that this seems to be on a fairly flat portion of the curve. And notice that the line got a little wider right here, but it's still 49, 50 knots predicted for my average cross-country speed if I've got 50% thermaling and 50% running. Okay. So that doesn't, that gives you a thing that if you're out here flying, um, you don't have to be quite as precise. It doesn't have to be exactly 87 knots. And if you're a little slower or you're a little faster, it's not going to have a horrible impact or a great improvement on your cross-country speed. If we pull back to our original at flying at best L over D, and now adding or now taking a look at where 10 knots slower puts us and where 10 knots faster puts us, notice that the small change, a 10 knot speed has a huge change in where these cross the line. So flying 10 knots slower has a huge impact, or flying 10 knots faster has a nice impact. The other one to notice with this, um, is especially in the older equipment, or especially if you're trying to fly your cross country at your best glide speed, that flying slower hurts you more than flying faster helps you. Okay. So the thing, when I said nothing on the right-hand side of the decimal point probably matters. If I change this to 4.2, it shifts it to right about here. If I changed it to 3.9, it shifts it back to right about there. Okay. So if you're flying a 10 knot, plus or minus 10 knot block speed, and you're flying up here in the McCready 3, McCready 4 range, uh, the decimal point on your McCready number doesn't really matter that much. I mean, mathematically it's interesting, but in terms of your performance in your glider, you've got to be back over here before it has an impact. And if you're back over here, you're not really worried about, you could be performing better over there. So what do you need in order total to fly speed to fly? You need a total energy variometer and you need a McCready speed ring. Okay, so I'm gonna bring the next slide up. Um, excuse me. So the this is the minimum to utilize your speed to fly. This speed ring right here. Okay, this one is calibrated for a duo discus. So here's your reference pointer at 0, and then and then these are air speeds that you could fly at. Notice it's nonlinear because that curve that we were looking at is nonlinear. So the spacing is greater from 100 to 120 to 140 to 160. All right. So this particular image is metric, so meters per second on the variometer and kilometers per hour on the airspeed. And right now we're showing just over 1 meter per second down, and over here we're showing 130 kilometers an hour. With this set at McCready 1, that point, the total energy pointer is pointing at 130, and so it's saying you should be flying 130 kilometers an hour, which in this case, that's what the pilot is doing. If there's better lift, if the day is going to be better, let's say that you said it was up here at a 2, you would fly faster. If the day is worse, you know, okay, or no, anyway, go ahead. So when the glider slows down to thermal, then this reference point, that becomes your where do I leave? When do I leave? So this could be set at a half or 1 or 1.5 or 2. Remember that meters per second, quick simplification, double it for knots. So this should be a 2 knot. This would be 1, 1.5 would be 3, and 2 would be roughly 4. So you could set this and say, if this drops, in this case, what they've done is they've said if this drop, if they slow to a thermal right now and they leave it here, they say that when the lift drops to 1 meter per second or 2 knots, the average up here drops down to that. That's when they leave the thermal. Okay. There are these speed rings that have dual numbers, and if they have dual numbers around the outer edge, that's so that one ring is the dry and the other set of numbers is the wet or the ballasted. So there it is without the writing over top of it. Okay, that's your bare minimum kind of equipment that you need in order, either that or you got to have pieces of paper with tables in it and stuff like that, this allows you to see it right on your instrument panel. And so your heads down time is heads down looking at the instruments, not heads down looking at a stack of papers in your lap. Now, what would you like to have? Okay. So now we start talking about speed to fly varios. And what we want is we want a vario that's got audio. It's going to be speed to fly, so that means it's got performance information about your glider in it. And we have some other indicators on here. So we've got a total energy, a netto or relative netto vario. All three of them will work. We have a speed to fly capability, and we have an audio. So in this case, again, this instrument, because where I pulled it from, this is in metric measures. So this is 2.5 meters per second. And so it's saying the average is 2.8 meters per second, so about 5.5 knots. And that currently we're at 2 meters per second. And the 129 kilometers an hour, this is a true airspeed, so that's saying that's roughly 70 knots. All right, the red needle, that's your instantaneous vario. The average on this one, this is, by the way, I believe this is it's an LXNAV S. They used to call them a V7, but I think it's what they now call an S7. This diamond is your average. Okay, so yeah, you can read the average right here, but you've got where's my needle with respect to that diamond? Am I doing better than average for this thermal or better than the current average for the thermal? The blue triangle, here's your McCready setting. So I have my McCready setting right in front of me, right where, so I can see when this drops down. It's easy. So that replaced that marker on the McCready ring that was out here on the side. The red arc, in this particular instrument, it was configured to be the range of the lift in the current thermal. And then the arrow over here, the circle right here is that this glider is circling. And then right here, this is your speed command or your speed director bar. And so it's saying it wants them to slow down. Okay, so even though they're thermaling, it's saying at this speed you need to slow down, pull up, pull up. Okay. I don't know what the green T is programmable. I don't know what they had it set for in that particular image. All right, one of the things that you have to have, or you have to know, a speed to fly vario does not know the glider's limitations. It does not know what stall speed is. It does not know where the beginning of the yellow arc is. It does not know where VNE is. Okay, so you never exceed speed. So when you're following the command bars over here, speed up and slow down, you have the responsibility to be aware of what your airspeed is because all of your safety numbers are all in indicated airspeed. So this thing will push you, the vario, the speed to fly vario is dumb. It will push you past red line if no, it will recommend you past red line. You're the one pushing and pulling on the stick. Okay. So what you've got to understand the limitations of what's represented here, in addition to, the really nice presentation it has for the information. The other thing that happens that we need to look at is the changes in the glider's performance as the mass of the glider increases. So again, a Venice B drive weight at up here, 346 kilos or 763 pounds, or over here at 500 kilos and 1,100 pounds. All right. The speeds and the sink rates vary between the two configurations, and the speeds and sink rates are higher when you're heavy. However, it's kind of interesting because when you start looking at it, the performance is not that dissimilar. Okay, so I'm at 64 knots heavy for my best glide, and I'm at something that looks like about 1.5 as opposed to 57 knots and 1.2. Okay. And as we move up, like in a McCready 2 situation, our airspeed over here is 72 with a sink rate of 2, and our airspeed over here is 84 with a sink rate just a little bit over 2. Now here's the interesting one. At McCready 2, we've got a sink rate of 35 to 1, and strangely enough, over here at 2.2, we've got a sink rate at 38 to 1. We actually are going a little we got a little better performance on our curve. If I push it to McCready 3, you can see things get interesting. But again, we're at 3 knots over here, 3 knots sink rate over here, and 3.2, something like that right there. And so I'll put these tables up. So as we go faster, the deterioration in our glide ratios, uh, we're getting an overall improved performance. Okay. So that's why you ballast up. Of course, the day's got to be good enough to support you being ballast up. Okay. And here's these two curves overlaid on each other. So the darker curve is the dry curve, and the lighter curve is the heavy curve. And you can see the difference in the best glide speeds right there. Okay, so one of the things that we have to know with MacCready is we have to know the mass of the glider. How heavy are we? And then there's taking it at MacCready 1, 2, and 3. And yeah, I'll back up just a second. There you go. So best glide at MacCready 1 and then MacCready 2. All right. Now the MacCready question. What's the lift likely to be in the next thermal? Today we're looking a little further out. Okay. And that is, how do I characterize the day? We're no longer just trying to predict what's going to happen in the next, let's say, 20 nautical miles. What does the day look like? And then how do I characterize my current circumstances? What is the minimum if we were in totally smooth air and no search time? In other words, it's easy to center. Maybe you center punched it and you managed to do your first turn and come right back into the core and go right up. So what is the minimum lift you would stop and take right now? Now, if I'm at 17,000 feet and I'm running 85 knots and I'm under a cloud street, I'm not stopping. But if I'm 3,000 AGL or 2,000 AGL and it's been kind of weak and maybe it's early in the day or maybe it's late in the day, yeah, I may not be in survival mode, but I'm in, gee, I'd like to have something mode. Okay. And then if we were trying to get home, how do I characterize the glide I'd use to get home? How does it look from here to get home? In John's webinar, he says how to fly faster. He says climb better, avoid bad lift, leave bad lift. And he says thermal effectively. Don't waste time sitting around in a bad thermal. Okay. No fishing, no going back. Okay. So if you've made a turn, you're probably and you're not finding it, it's better to go forward. And when you go forward, you move forward, don't go back because you just subtracted that time going back from your cross country speed. You don't need to thermal at high altitude. I mean, if you're up in that upper lift band, it's, you know, run like you stole it. Fly in lift if you can find it, and you cruise faster than your best L over D. If you check the flights on OLC, the long, fast flights have thermaling as a percentage of the total flight time in the teens. Somewhere around 15 to 20% of the flight is in thermaling. If you check your thermaling, download your flight and put it in CU or put it in WeGlide or whatever. Check your thermaling percentage. You're likely to find, if you're not a dyed-in-the-wool hardcore cross-country pilot, you're likely to find that you're thermaling somewhere in the 30 to 40% range for the flight. That's how much of your flight time was spent thermaling. So I always thought it was cute. It was kind of tongue in cheek, but John used to say he had three rules for how to fly faster. Rule one, climb better. Rule two, climb better. Rule three, guess what? Climb better. Efficiency matters. Okay, when you're climbing, when you're first flying cross country and you've proven to yourself that you can find thermals and climb, you can be a little bit sloppy, or maybe your skills are not up to it. But but efficiency matters, especially if you've got a long task and the day's, you're towards the end of a long task and the day's dying. So you want to avoid how to climb better. You want to avoid bad lift. Weak thermal lift hurts more than strong thermal lift helps. So if I said, what is the average of 2 knots lift and 10 knots lift? Half of the climb was in 2 knots and half of the climb was in 10 knots. Okay. So let's say you climb 2,000 feet and the first 1,000 feet, you were climbing at 2 knots. That took 5 minutes. Now you're climbing at 10 knots for the second 1,000 feet, and that took 1 minute. Okay. So you were climbing for 6 minutes for 2,000 feet. Your average is not 6 knots. Your average for that thermal is 3.3 knots. Okay. So two 4 knot thermals are better than, you know, that two 4 knot thermals are better than one thermal that covered the same altitude at 2 knots and then 10 knots as it improved. Now, one of the things to keep in mind is that you probably aren't going to ever hurt yourself if you're climbing in smooth lift at 5 knots. You know, don't bemoan that you're not in 10 knots. You're doing pretty doggone good. In terms of efficiency, your reaction time. So if you're running 60 knots, you're moving at 100 feet per second. At 90 knots, you're moving at 150 feet per second. If the thermal is 400 feet in diameter and you take 3 seconds to make a decision, by the time you've made your decision, I'm not talking about by the time you've moved the stick and the glider starts moving. I'm saying that if the thermal's 400 feet in diameter and you take 3 seconds to make your decision that this is a thermal you want, you may already be too late in finding that thermal. By the time the plane can move with its inertia, even coming back around on that first 180 degrees, you may not even hit the edge of the thermal. You may be well past it by then. So one of the things to consider is if the lift is not increasing when you're 60 degrees off course, it might be better to roll back out on your course heading and move on. Now, that depends on how desperate you are for that thermal. Some of your uh, other areas that you can do to improve, and this is probably the number one, is don't stop if you don't need the lift. Um, one of our club members sold his, I don't remember if it was a ASW-19 or a Pegasus, but he sold it to uh, another member when he was at another club back in another part of the country. And he was out flying. The new owner of the aircraft was a 126 driver. Okay. Now, I've often told successful 126 cross-country pilots, I can't fly to 126. I can't make decisions that fast. But the gentleman went out on they went down to Texas. I think they went down to Hobbs and, or no, Hobbs or Uvalde. So either Texas or New Mexico, take your pick. And he went out on a nice long flight and ended up landing out in his nice high performance glider and couldn't understand what he did wrong. Well, what he did wrong is he stopped at every thermal that he bumped into. And he didn't need to stop every time because the performance of the glider was so different. You know, it wasn't a 126 where you're only 5 minutes from landing, no matter what your circumstances are. This was a glider that could go much further. You know, we're comparing 22 to 1 to 38 to 1. But he wasn't taking advantage of the performance and he was stopping at every thermal. Don't stop if you don't need the lift. There's a psychological aspect. You have to have confidence that there will be lift ahead and you will find it. Remember my comment about John Campbell's search radius assertion. At 20 to 1, cross country is possible. At 30 to 1, it's likely. And at 40 to 1, it's pretty much definite that you've got the opportunity within your search radius to find a thermal. Now, your confidence is going to build when you get with a better understanding of weather and your experience. So one of the things in in trying to improve your confidence, why am I uncertain? Why am I scared? The other one to examine is how often have I actually landed, have I landed out from this particular, from this position and in this kind of weather? So if this is pretty much a good cross-country day, one of the things that you have to do is you have to develop the skills, the experience, and by skills, I'm talking about the flying skills and the skills for interpreting the conditions of the day and the experience, because, fly often. Um, you know, what you have to do is you have to build your confidence by building your skills and building your experience pool. The third one is cruise faster. Again, don't be flying at the best glide speed of the aircraft. And there's another thing that happens here, and I'm stepping outside McCready just for a second, but it's also another thing that we need to recognize. Long, fast flights use more than thermals. So you want to be looking outside for energy lines, cloud streets. Uh, uh, Very often in our part of the country, it's not so much a cloud street as it is a boundary line with clouds on one side and clear on the other. That might even be considered a convergence, but there's some kind of boundary line. Uh, Years ago in my Venice, I flew 75 nautical miles over the plains of Colorado without turning. That was my first long run without turning. And basically, what I was doing is I was following a real wispy, and I fly with the orange tinted glasses. If I took the glasses off, I didn't see it. If I put them on, I did. A real wispy boundary line. And that was my first long run without thermaling. And I came home and you know, I was walking on air. Um, and then not last season, but the season before, I flew my ASH 26 from my home airport. It's Kelly Air Park, which is between Denver and Colorado Springs, east to Hoxie, Kansas. That's 197 nautical miles, and I used three thermals for the entire flight. The first thermal was my initial climb at Kelly. My second thermal, I was just north of Lyman, Colorado, which is 45 nautical miles east from Kelly. I hooked up with an energy line. My third thermal was at Goodland, Kansas, 92 nautical miles east from Lyman. And I was setting up I decided, I'm going to I'm going to land at Goodland. And as I pulled the boards and I was spiraling down, and then I realized I had the boards out and I was climbing, and I said, "Oh, I can't. I've got to use this." So I closed the spoilers and thermaled on up and went to landed at Hoxie, Kansas, which was 60 nautical miles east from Goodland. So it's not just thermaling. Again, it's recognizing the weather and the conditions of the day and learning how it works in the areas that you fly. I'm lucky. I fly out here in the West, so we have awesome conditions. I've also flown back east. I flew for a short time out of uh, Front Royal in Virginia, and that was a real eye opener for me because I yeah, let's just say that was a real eye opener for me. I'm spoiled. All right, you're targeting cruise speeds in my Venice B. There's a lot of information on this, but I've got McCready numbers over here. I've got uh, green. I've got air speeds for dry and for wet. Okay. So basically, if I'm down and want to be, if I'm down using McCready zero, in my mind, I'm at imminent risk of land out. If I'm doing McCready 1, I'm desperate. If I'm doing McCready 2, I'm being cautious. Things are okay, but I'm McCready 3, that's my everyday setting. Everything I'm doing fine. McCready 4, I'm ripping, I'm confident. I may even be considered aggressive. Now, when you look at the airspeeds, all right, remember your airspeed limitations are in indicated airspeed. On the Venice, the yellow arc begins at 108 knots. So I got it showing at 106. I'm not going to argue 2 knots right here. So I show these in yellow. All right. In general, I don't fly uh, in the yellow arc because it's always supposed to be very smooth air. And at least where I fly, very smooth air is relatively rare. The other one is with the Ventus B, negative flaps above 86 knots. Okay, so that's the blues. Okay. Now, I'm always flying, I was always flying negative once I popped out of a thermal and ran up to, into the 72, 70, into this range, I was putting it in negative. I'm just saying this is the flight manual was telling you above 86 knots, put it in that, you're flying in negative. Okay. Now, the V&E on my Ventus is 135 knots, but V&E is derated based on altitude above the certification altitude. And you have to check that in your flight manual to see what that, see what those numbers are. The in CS22, which is the EASA certification document, the boundary between the green and the yellow arc is based on maximum gross weight. At weights less than maximum gross weight, the air mass acceleration could exceed the limits of the aircraft. Uh, because so anyway, it doesn't mean it will. It just says pay attention. You know, you don't want to operate outside the operating limitations of the aircraft because you're a test pilot. So keep the airspeed limitations in mind when you're using MacCready. Don't blindly follow the computer to higher airspeeds, especially at higher altitudes. Now, what do I mean by higher altitudes? If you fly from an airport that's 2,000 MSL, uh, you know, somewhere between 10 and 12,000 feet is a higher altitude for you. Most of the certification is done around 3,000 meters, or it's varied over the years, but 3,000 meters is a real common number. Um, I fly from an airport that's 7,000 feet above sea level. And so we're often near Class A boundary at 18,000 feet. So the glider can often uh, be well above the altitude that the V&E certification was accomplished. So most gliders, most modern gliders, there's a requirement that you have a V&E correction table near your airspeed. And some of the newer instruments, like some of the electronic airspeed indicators now have if you put the table into the airspeed indicator, enter the data into the airspeed indicator, then it will automatically adjust the red line to a lower airspeed based on altitude, basically based on the lower density altitude or lower altitude or lower air density represented by the higher altitude you're flying at. I'll get it out. So pay attention. Now, there's an average speed shown in here. And so, uh, that was based on that very early chart with something like 40% thermaling time. And so improve your thermaling and reduce the number of thermals and things like that, and life will get better. The Okay. Now, MacCready numbers uh, will generally transfer from glider to glider. So a MacCready 3 in a Nimbus 4 might be roughly the same amount of aggressiveness as a discus, but the L over D and the feet per mile that are consumed are going to be wildly different between the two. I mean, that's two wildly different performing aircraft. But the MacCready number will likely represent roughly the same kind of, uh, you know, scale like I have over here on the right-hand side. So basically, all of your cross-country decision making comes keyed to MacCready values from which thermals to take, how fast to fly, how aggressively to take your upwind turn points, and how big of a course deviation to take, and so on. The one thing that you do have to remember is you've got to look outside first for the answer. If you see the solution while you're looking outside, so like in a K-21 at 30 to 1, you're 5 miles out from the airport and you are 1,500 feet above the pattern, you very likely have that airport made without any problem. You don't need to be looking down at your computer and you don't need to be looking down uh, at your instruments as much because you can see the solution outside outside looking through your canopy. You can make your decisions based on that. You can tell if you're going to sink. You can tell if you're in lift, whether you need to speed up or slow down. So always look outside. If you can truly see the answer looking outside, you don't need to be looking inside. Now, this little approach was showed up in John Cochran's presentation, and he came up with this while flying a discus. Okay, so I think he's flying a 31 now, but anyway, doesn't matter. Maybe he's flying a 29. I don't remember for sure. Okay, so when you're looking at this, McCready that you're going to use varies with the altitude. So if you're low, you're using a low McCready because you're saying that's the thermal I will take. Okay. You know, and you work with your height bands. So if today this is 5,000 foot AGL height band, and these are all AGL, not MSL. If you're 5,000 foot AGL and you go, down to 3,500, so above 3,500, it's run like a scalded cat. And between 1,500 and 3,000, well, I can be aggressive, but I will take, uh, you know, I'll pay attention and take a good thermal. I don't need a thermal above 1,500, and I'm down here below this at 1,500 and below. I'm going to take anything I can find. And you notice with the McCready numbers, I definitely would take a McCready 1. I'd take a McCready 2. Okay. But if I'm up here, I'm not going to take a McCready 2 thermal. I'm not going to take a 2-knot thermal. Okay. I don't need it. All right. So, one of the things that you have to keep in mind is the needs and the behaviors at 18,000 feet over 7,000 foot terrain is very different than 9,000 feet over 7,000 feet terrain. And then, of course, obviously, if you're flying over, if you're a lowland flyer like you're down in Texas or you're in some locations on the East Coast, the luxury of saying, "Oh, I'm at 18,000 feet and I got plenty. I don't have to worry about it," is not something that was what flying at Front Royal taught me. Is the I had to change the scales in my mind tremendously. But basically, what this is showing you is, especially if I cast, a 3-level height band in here, you can see that the higher you are, the harder you can push is basically what it is, or the higher the McCready number, or the higher the lift has to be for you to say, "Oh, I'm going to take it." Changing gears. All right, I regularly fly an ASK 21 and an ASH 26. I don't have my Venice any longer. That represents a pretty wide performance and capability spectrum. And these are the guidelines that I'm using in a pure glider. Okay, in the previous slide, I was discussing reduce the McCready setting as you come down. Perhaps and that was John's terminology. Perhaps we should be thinking of it in terms of reduce the thermal strength expectation or reduce the pilot aggressiveness setting. Okay, so, and this is where some of the stuff that comes out of the bronze badge training carries forward even when you're an experienced cross-country pilot. And that is, you need to set some thresholds where you are making decisions about uh, your circumstances, that you need to change gears. Okay. Now, you may change gears at much higher. By the time you're down to 3,000 AGL, you should have backed way off from what you were up at 5,000 AGL or 6,000 AGL. Excuse me. So I'm flying west. I'm flying in the west out here, and I'm flying a pure glider. So at 3,000 AGL, I back off on my McCready setting, or I back off on my thermal expectations. I want to have a landable location available. and my focus becomes finding lift. Okay. And at 2000, I'm going to back it off again. I'm going to select the landing location that I'm going to use. Up here, it would be nice if I had several. Okay. And ideally, one of them arranged on my course line. Down here, I've selected where I'm going. And this is what I call my last stand range. I select where I'm going. I make a determination as to how far away I will get from that location in my search for lift. And then I'm at 1,000 feet. I say reduce McCready setting. Forget it. McCready no longer matters. I'm doing an inspection of the landing location. I'm still searching for lift, but if you're an early cross-country pilot at 1,000 feet, you should have already inspected and your gear should be down and you should be in a pattern, flying a pattern that you're comfortable with because you generally fly your pattern at your home airport starting at 1,000 AGL. Okay. Experienced cross-country pilots can take this down to a lower number. I'm not going to give a recommendation. But the whole thing is you are past your last stand and searching. You are either in the landing pattern or you're running your landing checklist and getting ready to enter the landing pattern. And remember, aviate, navigate, communicate. Regardless of anything else, don't pick up the mic. Don't, start checking instruments. You fly the aircraft. When you're down in this range, your job is to safely operate the aircraft. Everything else is, and actually I would put, you know where you're going. There's no navigation, there's no looking at a map, there's no this, that, or the other. And at this point, if you've committed to making a landing, you've already said, you've called whoever's out there, hey, I'm landing out. But past a point, your job becomes purely aviate. Don't get distracted below that 1,000-foot level. Now, I also fly a motor glider. So how does this change when I'm in a motor glider? Okay. So I'm 3,000 AGL. I reduce my McCready setting. I dial back my aggressiveness. I dial back my expectation on the thermals. I make sure that I've got a landable location available. I'd love to have multiple. The other decision that has now been added is I decide if using the engine is viable. Okay, if the whole area is in strong sink or very strong winds, using the engine may not do anything useful. And if you've got a plummet to start engine, in other words, you have to put the engine out and then dive because you don't have an electric starter, you're going to lose, 300, 500 feet. So, you know, if the conditions are not decent, do you really want to give up 500 feet to start the engine? Okay. So you decide whether or not the engine use is viable. And the reason you make that decision here is because if you've said, yes, I'm going to use the engine, or no, I'm not going to use the engine, then that affects what happens when you're down here at 2,000 AGL. Because now I've selected the field and I've got to be close enough to that field that when I throw the engine out, if it doesn't start, I can make the field and land. And I do my start sequence. I'm configured and do my start sequence at 2000 AGL. That way I have the option. If the engine doesn't start, I can leave it out and land. Or if it doesn't start and I've still got enough elevation, I might be able to put it away and, if I bump into, but if it doesn't start, you know, I'm landing. Rule one, you're landing. Option one, you're landing. Be surprised if the engine starts. Now, I'm a gearhead. I make sure that my engine's reliable. I make sure it will start. And yes, much effort as I put into it to make sure that my engine is reliable and it always starts, I did have a time when I deployed the engine and I couldn't get it, I could only get half the rated RPM out of it. I had a fouled plug. The first start of the day worked just fine, but later in the day when I went to start the engine, I had a fouled plug and I couldn't generate enough power to climb out. So it was put it away and land. And you don't always, check your flight manual, but I don't know of any motor glider that says you can't land without that prohibits you from landing with the engine out. I know of no glider that says that. So, uh, and so the safest thing to do is if it won't start, don't try to put it away. Just go ahead and land because you're in the condition now. You're an 18-to-1 glider, at least in my Ventus. There are others that are worse. There are some that are a little better, like the modern electrics. The engine doesn't represent any load at all because it's an electric motor. But the whole thing is that don't distract yourself down here because now you're going to have, something failed and you've got to get yourself into I'm landing. Okay. Now, one of the things is if you're in a self-launcher and you're down low, you got a decent location, like a real airport, land, get off the runway, go over to the FBO, get a soft drink, go to the bathroom, and then say, okay, let's see if the engine will start. And if it does, you could take off and fly home. I have a cousin that had that happen with his glider. He had a brand new super glider with self-launcher. He launched and went out and flew and had a good day, was getting low, put the engine out to start it, and it wouldn't start. He had a nice field. It was a very good field. He landed, got to rolled out to the far end of the field, and lo and behold, the engine started. It turned out that the wind load on the pylon with the engine not running was enough to keep it from triggering the pylon deployed light. So, on the ground it started, and with the load from the propeller pulling the pylon forward, he was able to launch and get home and have his mechanic take a look at, because he saw that the deployed light didn't come on. So, you know, especially with the self-launcher, you know, go find a safe place, land, and then consider whether or not you want to launch and take off later. McCready settings, lower McCready settings. Okay, why do we use McCready 3-4 in 6 to 8 knot lift? Okay. All right. First off, we've got centering time. We've got thermals that vary with altitude. So like this one, it's 3 knots, then 4 knots, then 6 knots, then 7 knots, and then back to 4 knots. Interesting. The other one is that the thermals move. So like what I'm showing here is that this thermal is moving slightly to the right as it goes up in elevation. The other thing is when you look at this, yeah, you called your buddies on the radio. Wow, got a 7-knot thermal. This is not a 7-knot thermal. The thermal rating is either the lesser of the initial climb rate, so 3 knots down here, or the total getting from the top to the bottom. And most of your flight computers will give you a number that will tell you how much you gained in that thermal, and divide that by the time, and that tells you what your climb rate was, regardless of what you saw on your instrument. Now, you'll always remember that 7-knot thermal, but analyze your trace after the flight to see how you did. And like I mentioned earlier, I use CU on my PC at home. WeGlide, which is offered with the SSA membership, has a suite of analysis tools to help you understand your flight. So that's why you may be flying a 3 or a 4 when it feels like it ought to be a 6 or 8 knot day. But if you set it at 8 and you're running along 1, if you set it at 8, you're probably up in the yellow arc. And 2, if you're bombing along that fast, you may never find the thermal. I'm not saying you can't. I'm just saying you might not. All right. That's the adaptation for modern flying as opposed to just using MacCready to get from one thermal to the next. Uh, the safety glide, our speed to fly for final glide and our speed to fly to get over uh, untenable terrain. A lot of folks believe that if they're on final glide, they fly MacCready zero, and that's what they should be flying. Of course, if you do the speed to fly for MacCready zero, you're at your best L over D, your best glide rate. And they think they're being conservative, and actually, this is a very poor choice. So a safety glide can be a final glide. A safety glide can also be any glide over terrain that landing out poses a real problem. First thing that you have to do now is you have to truly understand what your instruments are telling you. You've got a speed to fly vario. Okay. That means that the vario understands the performance curve of your aircraft. That means that it has a speed director that says fly faster, fly slower based on the lift and sink that you're in. So it's going to give you an indication of fly faster, fly slower, or things are just right. You're going to have a glide computer. The glide computer uh, is going to establish the glide plan, and I'll delve into that a little more. And then the other thing that the glide computer is going to do is it's going to monitor your execution via a glide slope indication of some type. Both of the devices use a MacCready value. So you're setting a MacCready value in your glide computer, you're setting a MacCready value in your speed to fly vario. Okay. So we're going to be working with a day. We're going to be talking, we're using MacCready 4. And so we've got, uh, so if I go down in 2 knots in sync, I get 2 knots better, or I get 2 knots worse. That's what these two are. Okay. So we're going to bring in the speed to fly vario. And so the MacCready 4, it's going to tell you that when the lift improves, you want to slow down, and when the sink gets stronger, you want to speed up. And that, here's the speed that that's, and like the speed director bars I talked about on that S7 many slides back, it's going to tell you to pull up or push down. It's going to have a bar over here. You may have another one. You may have a on some of the more advanced computer Varios, you may actually have a number there that it's telling you what airspeed to fly. Okay, not just the MacCready number. So the speed to fly knows nothing about altitude. It knows nothing about distance, and it knows nothing about the glide ratio that you're trying to fly for the solution to get to your landing. It knows what you're doing on your performance, but it doesn't know that you're trying to do final glide as opposed to doing an interthermal flight. The information about altitude and distance and that kind of stuff and setting the thresholds for the glide ratio, that's the glide computer's job. It just tells you how to respond to changes. The Vario tells you how to respond to changes in lift and sink with reference to the desired MacCready number's speed number. So it's going to tell you to speed up and slow down based on what it sees as lift and what it sees as sink. Now we have the computer. So if we set the computer at MacCready 4, so we've set it at 4, see the purple line right here. Okay, that establishes the glide ratio that is adjusted for bugs and ballast. And then as you're flying, you've got almost all the computers have an indicator on them that tells you how you're doing with respect to the glide slope that you're on, and it adjusts for altitudes and winds. So if you're flying into a headwind, it's going to adjust it as you're coming down in altitude. So this performance monitor is telling you how well you're doing. The computer is not accounting for lift or sink. The Vario is accounting for lift and sink. Okay. Now, one place that you have to be careful. Some systems, for instance, uh, the 302s, they allow the glide computer to set the MacCready value in the speed to fly Vario. And I'm going to show you in a couple of pages why you don't want that. You want them operating on two different numbers, and I'll show you why in a few minutes. So if you've got a system to where if you set the glide computer to MacCready 4, it automatically sets your Vario to MacCready 4. You want to find out how you can turn that off. You might want that for your normal cruising flight, but when you're doing the safety glide, so your final glide or your glide over uh, undesirable terrain, you want to be operating with two different MacCready numbers. And I'll explain that here shortly. The other one is that MacCready theory assumes that the lift and sink balance out over the course of the flight. Now, when we come to final glide or we come to the safety glide, this isn't the average over the whole day. This is the next, let's say, 30 minutes. You know, give you a final glide from 30 miles out. This is the next 15 to 20 to 30 minutes. So the lift and sink are not necessarily going to balance in that time period over that distance. So that's where it starts to fail. Now, here's our MacCready number. Here's our dry speed to fly. I mean, if we're really down and we're scraping and trying to get home or we're trying to get out of somewhere, we probably aren't holding on to our ballast. And here's the glide ratios that are associated with that setting and the setting, the resultant airspeed, and here's the glide ratio that's tied to it. And this is where the modern usage differs from the traditional usage. And this is the same slide that I presented earlier in the presentation. If you see it, you go back and look. Okay, so the traditional usage is a strategy for interthermal speed. Both the glide computer and the speed to fly Vario are using the same MacCready setting. In this case, the strategy for the safety, the final glide, safety glide, however you want to look at this. And again, I saw this first in John Cochran's materials, and I had a real aha moment when I finally understood what he was telling us. The glide computer and the speed to fly variable are set for different MacCready settings. So you're 30 miles out, you're coming in for your final glide. It's been a nice, strong day, and you dial in MacCready 4 on your computer, and the computer says, you can make it home. You've got final glide. Congratulations. Okay. But I want to have some margin. Okay. Always put some margin in the bank. Whether your bank is altitude, whether your bank is speed, whatever, always have some margin in the bank. I don't need to be flying 87 knots. So I'm going to set MacCready in my speed to fly Vario at 2. And I'm going to put, my block speed, I'm going to fly based on a 72 knot speed to fly. Notice that I'm flying with my Vario, assuming a 36-to-1 glide ratio, and the computer is saying I can make it at a 29-to-1 glide ratio. There's my buffer. Okay. If I'm 30 miles out and I say I'm going to fly McCready 0 at 43 to 1, where's my buffer? I don't have one. If I run into more sink than anticipated, I can't change anything to help me get home other than to find lift. And I'm assuming right now that I might not find lift in this next 30 miles. So we're over uncomfortable terrain. Your cockpit computer is generally looking to finish with minimum excess altitude because your computer is, it's supporting contests and general cross country. Okay. That's not our issue in a safety glide. So that's not our issue on a final glide. That's not our issue over uncomfortable terrain. So you're going to use two different sources of information to manage your glide. You've got the speed director that's in your speed to fly vario, and you're going to use the glide computer. Hopefully you guys are reading the slide down as I'm talking. So you're going to set the speed director. In this case, what my example is at McCready 2, so you've got a 36 to 1 glide ratio, and you're going to set the glide computer to McCready 4 at 29 to 1. The computer says you can make it. If your progress stays above the glide slope calculated by the computer, in other words, I keep a better glide than 29 to 1, you'll make it. If you're descending towards the safety glide slope, the speed director, you might want to dial it down. We're getting closer. I'm not finding any lift. I'm not really sure I can divert. I'm kind of committed. Well, if I dialed it down to 1, then the speed director is working at 41 to 1, and you're still working at 29 to 1. Now, you also may end up dialing this down, to see what it's going to do. But basically, you want to keep your glide computer on McCready 4. That's where the decisions are made, whether it's a go or no go. In other words, go on or divert. Okay. If you're, what do I have within that circle, within that search range? Okay. And so we're going to work through all of this. The key to remember is that when the computer up here is saying push to 87 knots and you'll finish, at 1,000 feet above the field, that's not your question. The 29 to 1 profile is for safety. It's not for speed. It's not for burning off the excess altitude. It's there so that you have a margin for safety in case there is sink along the way. So the goal is to fly a slower, better glide and then adapt to lift along the way. Okay, and the example I'm using is McCready 2, 72 knots. If the glide computer sets McCready 4 on your speed director, on your speed to fly vario, the vario will be making its recommendations based on McCready 4, based on the 80, the uh, 80, I lost it, the 80 plus knots, not on the 72 knots. It's going to be constantly complaining to speed up, and you will lose any indication in your speed director reference to the McCready 2 value. You've got to decouple the speed director from the glide computer. So your speed to fly vario has to be running on its McCready setting, and the glide computer is running on a separate McCready setting, its own McCready setting. That's the key here. So conditions are good enough that we're assuming that we have a good safety glide solution at McCready 4. The computer establishes the clearance plane. Okay, that's the purple line. The speed to fly vario is going to get set at 2, glide computer at 4. Notice I've got a green line. That's the glide slope associated with McCready 2. There's our margin, the difference between those two. So as long as I stay, let's say there's no lift or sink on where you got a flat day and we're coming in, our glide ratio will keep that margin all the way home. Now notice it gets smaller down here, but when we're just a couple of miles out, we don't have to worry so much. Okay, it's the gap between these two lines. And then you have the glide slope indicator that's on your computer, and you use that to monitor your progress. So each device is using its own McCready setting. If your progress is not as good as it was, and you need to slow down to improve the glide ratio that you're using, then dial this guy down. I don't think I'd ever go to zero. If it was getting that bad, I would already have been working. If I said that I had to reduce my speed to fly vario, for instance, in the example I'm using, I started at 2. If I said I need to reduce that from 2, I would have started, I would have said, okay, I need to divert to one of my alternatives. Okay. Now, the key to remember is that every time this McCready number changes, the airspeed that you're using as the basis changes. So you may need to have a little chart with McCready setting to speed to fly somewhere to help you remember that, the 87 that it's telling you it wants for McCready 4 is not the number you want to fly. Now, that's because most Varios don't, or a lot of Varios don't have that, the speed to fly airspeed, excuse me, displayed. However, I do know that the LXNav S80 and S100 family of Varios would allow you to configure so that you can have the speed to fly airspeed on the instrument. And that's what I do in my glider as a reminder uh, of what airspeed I want to use when I'm doing this kind of a glide. Okay, when we're looking at all of this, uh, you don't use a table like this in the cockpit. This is a pre-flight exercise to help you get things firmly fixed in your mind about how you want to approach. Okay. Um, Most of us, when we're flying, we think in terms of either L over D or we think in feet lost per mile. Okay, the computer is talking, what we're setting on the computer is McCready numbers. If you create a table like this for your glider, you can go in and say, oh, I want a day that's got an average speed of 54 knots. Oh, that's McCready 5 day. Okay. You can play this back and forth across the whole spectrum. Um, but the key in having a table like this to help you understand is, you know, your the glide speed and the L over D and the feet per mile. And again, why I use nautical miles is because, if I divide, you know, I'll pick an easy one. If I divide uh, 200 into 6,000 feet in a nautical mile, I'm using 200 feet per nautical mile. I'm roughly 30 to 1. Okay. So you can use this to convert McCready numbers to these other numbers so that you can play with them. This is not an in-cockpit exercise. This is something you do on the ground. Okay, so 29 to 1 sounds like a reasonable safety glide. That's McCready 4. Standard safety recommendation, for instance, you go to fly in the Alps and you're going to find out that the instructors there are going to say, your standard safety recommendation is 20 to 1 glide ratio. Okay, for instance, in my Ventus, that's McCready 8. Okay, now we're not talking about final glide, we're talking about safety glide. This is the terrain is unlandable. What do I need to use in order to not determine the speed I need to fly, but can I get to a safe spot from here? Okay. And so if I said it had to be 20 to 1, I dial in a McCready of 8. I have no intention of flying the speed associated with McCready 8. What I'm looking for is that 20 to 1 number and to see what's available to me within that 20 to 1 circle around my aircraft. Okay. So when you're doing untenable terrain, you need to be using numbers that are larger, or you may need to be using numbers that are larger because oftentimes you're in the mountains and things move very quickly there. We have, like for the folks, our folks, when they're going their first forays back over into the mountains, we tell them don't go past the Front Range unless you're 15,000 feet. Because at 15,000 feet, even if you're a couple of miles back in, you've easily got the ability to cross the Front Range of the mountains and to get to one of like three or two or three or four airports, or I say airports, they're actual landing strips, but you have the ability to get to several landing strips from that altitude from several miles behind the edge of the mountains. Um, so that's a rule of thumb that's trying to do this same kind of thing. So the other thing that you have to remember with this is you're using these high numbers because our modern gliders are so highly optimized. They sink so little in still air that even what we would say is small amounts of sink can have a disastrous result on the overall glide angle. So 20 to 1 is what I need to use for safety. Okay. I don't care about average cross-country speed. I don't care at what speed it says I should be flying this. I want the 20 to 1, and then it gives me solutions to the various targets around me. My computer will give me solutions. Do I have something usable within that range? Okay. Your question here is not what speed should I fly? Your question here is can I get home from here? And you're using the MacCready mechanism to help you evaluate the answer to that question. Okay, we're back to my Venice polar. So here's my polar. Let's drop my polar by 2 knots. I'm in 2 knots of sink. Okay. My glide ratio went from 53 knots to 72 knots. I just went from a 43 to 1 glider to an 18 to 1 glider. So if I'm in sustained 2 knot sink, my my progress over the ground is going to be as an 18 to 1 glider in that sink. So you can play the game. In this case, I'm going to shift the chart slightly. This is a netto, so this is the atmosphere around you. Uh, and so MacCready 0, this is your best angle. Assume the pilot's desperate and he's flying MacCready 0. How bad is his glide in sync? Okay, it's horrible. Okay, in 1 knot sync, if he's flying, he's flying MacCready 0, so he should be a 43 to 1 glider, right? He's in 1 knot sync. His glide ratio is 25 to 1. In 2 knot sync, his glide ratio is 18 to 1. In 5 knot sync, his glide ratio is 11 to 1. That's worse than a Cessna 172 with a windmilling prop. Okay. So the other thing that you have to take into effect is whether or not you uh, you think that this is a line of sync. There are lines of sync as well as lines of lift. So, and if you're on final glide and you get into a line of sync, yeah. Okay, so this illustrates why you don't want to use MacCready 0. You don't want to use MacCready 0 and peg it there because if you're in sync, you're not 43 to 1. Don't use MacCready 0 as your computer setting for final glide. Now, we're coming in for our final glide. How high do I have to be out here? All right. The dash lines are set up for a ASG 29, and the curved lines are set up for my Ventus. Okay. The blue line is a McCready 2 line, and the red line is a McCready 4 line, this line right here. Okay. Again, this is a pre-flight. This is an on-the-ground exercise. So the if I if I fly McCready 3 all the time coming home and I blow one or two final glides in a decade, that doesn't mean I need to jack it up to McCready 5 and have it, I don't need to jack my mechanism up to McCready 5 to ensure that I get home. Okay. Um, this analysis is a statistical analysis. John Cochran came up with it. And again, this is one of those aha moments for me. So if we make an assumption, that's this blue line right here. If we make this assumption that for every mile you fly, there's a 1/3 or 33% chance that you're going to lose 100 feet more and a 2% chance you're going to lose 200 feet or more. In other words, you're flying in sync. So it shows how many feet over a McCready zero. This this shows how many feet over McCready zero you have to be in order to make it home. Okay, and that's basically trying to keep his boundary was a 2% chance of land out. So if you're 1 mile out, you need 200 feet over McCready zero. At 20 miles out, interestingly enough, you don't need 20 times 200. What you need is something around 700 feet, 600 to 700 feet out here. It's not 2,000 feet up here because it's not a linear relationship. And his analysis is based on it being nonlinear. Now, one of the things that he says is that you need, if you're 20 miles out, you need uh, the square root of 20 times 200. So if I needed 200 back here and I'm 20 miles out, I need the square root of 20 times 200. So in that case, it's like 4.5. So you would need, uh, you'd need to be up around 900 feet. Okay. And that would get you home. Most likely that would get you home at McCready 3 if you encountered occasional 1 knot and occasional 2 knot sink on the glide home. And then this is the same number, looking at McCready 5 or same curve. So the key with this is that the idea is that he's not factoring any additional lift. What's being said is how much does sink affect my ability to get home? And I'm only losing, if I'm losing 200 feet in 1 mile, but what's the chances of losing 200 feet over the entire 10 or 20 miles? And basically, what it boils down to is that's kind of like flipping a nickel and having it come up heads 10 times in a row. But it does say that, oh, it might, statistically, we should see it average out at 5 times, though. So there is, this is accounting for sink, but it's saying that it's not continuous. Now, the so why we're using the higher glide angles like McCready 4, 3, and 4 or 5 for the final glide is to give us margin to get home. The problem with this particular analysis is what happens if you get in a river of sink, just like you get in, if you hit an energy line that is sink rather than lift. All right. And, if you want to learn about them, follow me around sometime. I have this tendency to find them. I try to get out of them, but I do have a tendency to find them. Okay, reality is somewhere in between no sink and sink the whole way home. The idea is to use a McCready setting. So, 3, 4, 5, for the computer and then an associated uh, higher glide ratio McCready setting for your speed to fly indicator for your vario to improve the results of getting home. I mean, the whole answer is it depends on how far out you are. So, but you don't need, there's one that says, oh, add 1,000 feet for every 10 miles that you're out. Okay, this one added 1,000, made it 1,000 feet total at 20 miles out. And of course, the thing about adding 1,000 feet every 10 miles out, that sounds good, but the thing that you run into is with that is that you end up bumping against Class A airspace. If you're 50 miles out and you say you got to add 5,000 feet, um, you know, at least out here where the ground's seven, 50 miles out, I'm 5,000, the ground level's 5,000 feet, and I need to be 5,000 feet above my glide slope to get home. Nah, I'd be in Class A airspace. So the real thing that happens here is that if you follow this, using the square root of the distance to add to the 200 feet back here, if that's what the McCready zero number is at 1 mile or 2 miles, that kind of thing, then at that case, that will almost always, you get that rule of thumb established, that will almost always allow you to get back in with some margin. And I mean, the whole purpose behind this is to get home safely, right? So, what values should you use in the real world? Okay, so we're talking about the computer setting. The vario is up to you. How you fly is up to you. And the standard answer, especially from an engineering background, is it depends. It depends on the cost of not making it to your desired landing point and consequently what probability of not making it you can accept. Okay, so we're doing casual cross country. Maybe we're doing contest cross country. If you're doing casual cross country, you're flying over good fields, the cost of a land out versus making it to an airport is only inconvenience. All right. So in halfway decent conditions, the speed to fly vario, uh, set the computer to uh, 4 and set the speed to fly vario to 3. A weak 1 and a knot, 1 to 2 knot lift, build up some margin, set the computer to 3 or 4 rather than McCready 2 of the last thermal. Set the speed to fly vario something lower. Okay. And especially if it's like late evening where, things have gotten weak, the lift has gotten weak, but the sink has gotten weak, build up a margin. Remember, you're not flying the McCready for the computer. You're flying the McCready on the speed to fly. You're flying the airspeed associated with the speed to fly vario. In rougher terrain, okay, the cost of landing out could be damage, but not personal injury. This argues for a good deal higher values, maybe in the McCready 5 range on the computer. Remember, you're not flying the McCready 5 airspeed. You're likely flying either a McCready 2 or a McCready 3 airspeed and following your speed to fly vario. Again, you fly faster to get out of sync. If you're in the uh, totally unlandable terrain, you're crossing it, where failing to make your goal might be injury or worse. That argues for a very high probability standard. This is going back to the instructors in the French Alps telling you to use 20 to 1 plus reserve. Okay. That might mean a McCready at 10. And, don't be surprised if your computer doesn't know what McCready 10 is. There may be an upper limit in your computer. Again, you're not flying that McCready 10 airspeed. You're managing your performance against a McCready 10 glide slope. I've used the techniques that we're talking about this evening ever since 2019. That's when I finally pulled it all together and got it firmly fixed in my head. I fly into my home airfield. Normally, I start McCready 4 and McCready 3 on the Vario. Um, and McCready 3 and McCready 2 on the Vario. McCready 3 on the computer and McCready 2 on the Vario is not unusual. Most of my final glides start about 20 miles out, but I have done final glides from 50 miles out. That's not unusual out here in the western U.S. I'm on the front range of the Rockies, and conditions out here can be awesome, both on a positive side and on a negative side. And to give you an idea about how you approach some of this, a couple of years back, a friend and I happened to be returning to the airport from the same general direction. Basically, it was a long day. He flew much further and much longer than I did, but basically we used the same turn point for our last turn headed home. He was in an ASG 29 and I was in my ASH 26. We found ourselves near each other about 40 miles out at roughly the same altitude, separated by a couple of miles. Okay, he is a dyed-in-the-wool cross-country animal. He is the standard that we aspire to be. Okay. So he flies faster than I do. So he increased his lead over me while we were headed home. I have no idea how he manages his final glide. I've never sat down and said, how do you do it? Because I've come up with a system that works for me. And so, but he normally makes it home. So his method works for him. I normally make it home. So my method works for me. About 20 miles out, I decided I wanted a little more altitude. Now there is a performance difference between an ASG 29 and an ASH 26, especially at 18 meters, but they're still fairly comparable aircraft. But I decided about 20 miles out, I wanted some more altitude. I found a nice thermal, added roughly 1,000 feet to my altitude bank. I felt good about it. My friend continued on without stopping. He made it back. And when I got back to the airport, I had an extra 1,000 feet over what the computer indicated I would have had prior to that last thermal. I snickered as I opened my spoilers. I lit down to the pattern altitude. I didn't need the extra altitude after all, but so what? It was a nice low stress final glide, and that definitely counts for something. For final glide and sustained stink, you need to use McCready values like McCready 3 plus 200 feet, 250 feet times the square root of the distance out for 1 knot sink, and McCready 5 plus 300 feet times the square root of the distance for 2 knots sustained sink. Let's try that again. Sustained sink. You will routinely get to your goal with gobs of altitude, but we're doing this for fun. There's nothing there that says risk your life, especially if you're crossing unlandable terrain. So yes, that's the point. Get home with altitude in the bank. You know, that way your plane doesn't have to go to Fidel's shop in Moriarty, and you don't have to visit the emergency room. Give yourself margin. So when you're looking for the version of McCready that I'm talking to you about this evening, at any moment, what is the weakest lift I would take right now? Set that to your McCready value. I use this scale um, that helps me guide the settings that I would use. So 0, imminent landing, desperate, 1, 2, cautious, 3, every day, 4, aggressive. When I get into 5 or 6, it pushes me into the yellow arc. I don't fly into yellow arc. Take any lift stronger than the value. Leave in any lift that is weaker. Leave now. It's not worth it. You've got a corresponding block speed, so you never fly your best L over D. You fly the speed that's indicated, and then you have this range around it. You can set your block. A lot of people use a plus or minus 10 knots on that so that it's not constantly, pinging you about speeding up and slowing down. Your McCready setting depends on the weather that you're flying in, the conditions you're flying in, and the terrain that's ahead of you. You reduce your McCready expectations. I say value, but what I say earlier, reduce your expectations for the strength of the thermals you're going to find and reduce your personal aggressiveness as you get lower. Increase the McCready setting as you get higher. You can expect better thermals. Uh, I don't think you need to get more aggressive as you get higher, but you know, sometimes you get up there and it's going really great, and you really do have to dial yourself back when you come down, when you get lower. Leave bad lift when it's safe. That's one of the things that doesn't get talked about enough is that I'm down low and I got this 1 knot thermal or this 2 knot thermal. And so that's not great lift, but if I leave right now, I'm landing out. So use that to get you up, get up a couple of thousand feet, and maybe you can search a little bit for something better. Stair step your way up, that kind of thing. Use use a McCready much higher, your McCready value much higher in your computer for safety calculations. Make this automatic. Okay, speed is mostly about climbing better, avoiding a search on your turn on your thermal. It's about reading the weather, it's gliding and lift, and it's avoiding getting stuck. And I have to say I fail on that last phrase in that sentence. I have at least 1 or 2 times every year I manage to get myself stuck somewhere. I get home safely, but I have 45 minutes or an hour where I'm going, why did I make that decision that got me here? And then the other one, climb better. Like John said, rule 1, 2, and 3, climb better, climb better, climb better. All right, as we look at this, all models are wrong. Some are useful. Okay, so McCready theory is built around a model of performance of the glider and how the day is and your abilities as a pilot. There's enough useful here that makes McCready, that we're close enough on the modeling that it makes the McCready theory useful for flying faster, efficiently, and effectively. Okay. A 70 knot average cross country speed, so 100 and what, 15, 120 kilometers an hour. Efficient thermaling, gliding and lift, and it doesn't come from booming thermals and mad fast glides. Okay, it comes from using the day, not fighting the day. And I can't really emphasize this enough. Don't put McCready 1 or McCready 0 into your glide computer when you're trying to get home for final glide. If you put McCready 3 in and it says you can't get there, then what you should be doing is looking for an alternative, either another landing location or searching for lift. You're not ready for final glide, you know. So, but the real key is that don't fly McCready 0 or McCready 1 on your final glide because you have no margin. You might make it home, but you have no margin. All righty. Questions?
Dave, we've only got one question here right now. It's from Richard, and I think you kind of answered this a couple of slides back, but he's asking how often do you adjust the McCready settings in flight, and what conditions or changes in conditions should I be looking for to want to change the McCready settings?
Okay, I'm the casual cross-country pilot, not the contest pilot. Even though I do fly in contests, but I keep making the statement that I fly in a contest so somebody else doesn't have to finish last. All right, so carrying that, I don't change it all that much. When I do change it, it is, uh, I do the setups when I think I'm ready for final glide home. The other one though is you have to watch the day. Um, where I was out a couple of years back, I was about 60, 70 miles out from the home airport, so a little over 100, a little over 100 kilometers out. and I got to watch the day change around me. A front moved in from the east. I was way out on the plains up in the northeast part of the state, and I got to watch a front move in, and where I had been flying in the McCready 3 to 4-ish range, when that front moved through, I had to back it down desperate or dramatically because the lift became very few and very far. It was weak, and there were fewer points, and it was much further apart. And I had the same thing happen to me last year. I was about 150 kilometers southeast of our airport, and I had been following a frontal boundary going out, so running the lift line going out, and it was a fantastic flight. And I got out, I turned around because I was doing a 300 out and return that day, and I turned around and realized that the north north of me coming back home, I had to go northwest coming back home, that the boundary had moved so far west that I really couldn't follow it because it was going to go into some Class C airspace and that kind of thing. And I could see the change. I could physically see the change in the atmosphere. Again, I fly with the orange tinted glasses, so I can see haze domes and stuff like that. But I got to watch the atmosphere change and had to dial down my expectations. But normally, you know, I leave the airport with, again, I'm flying out here in the west. I leave the airport with 3 or 4 set in the glider, and it pretty much stays there until I'm ready to come home, unless I run into changing conditions like that.
All righty. Thank you, Dave. That's all I've got for questions.
Yeah, I'm not a I I'm not a fiddle with the McCready every 30 seconds kind of person. All right, next time, collision avoidance technology. Um, March 26th. So same bat channel, same bat time. Thank you, everyone. Have a good one, and we'll see you in 2 weeks.